Hello, today's lecture is lecture 114. It is the frequency response of a low-pass RC circuit filter. Just for a little review, an electrical filter is a circuit that permits electrical signals having certain frequencies to pass from the input to the output while blocking all others. That is, it filters out all frequencies but the selected ones. There are three types of series RC filter, two that can stand alone, while the last is a combination of the first two. We begin with a passive low-pass series RC filter as seen in figure 1. As you can see, the analog signal in hits the resistor and drops the voltage across the capacitor. So as the reactance here is high, we have voltage out. As this frequency increases, we know that the reactance decreases, and thus that steers the signal to ground, producing this Bode plot we have right here. We know that the 3 dB point is found by equation 1, which is equivalent to frequency cutoff is equal to 1 over 2 pi RC, producing this graph here, making a low-pass filter. The circuit is called a passive circuit because the components within the circuit receive and process electrical energy but do not generate or amplify the signal. The output of this circuit is across the capacitor, and as the frequency of the input increases, the capacitive reactance decreases, steering the input signal to ground. The second circuit is called a passive high-pass series RC filter, as seen in figure 2. Here, the capacitor and the resistance are changed, and the analog input hits the capacitor first, and the load or the voltage is dropped across the resistor. Now, as the frequency of the input increases, your reactance of your capacitor decreases, forming a short, and then thus dropping all the input signal's energy across the resistor, forming this type of Bode plot. And the 3 dB point is right where we said in equation 1, Fc equals 1 over 2 pi Rc. And this would be the high-pass filter with a cutoff in the low frequency range. The output here is across the resistor. As the input frequency increases, the capacitive reactance decreases, allowing more energy to drop across the resistor. And remember that while the input voltage is zero frequency, the output voltage is 0 volts because the capacitor blocks direct current. It only passes displacement current. The third type, a series RC filter, is the passive bandpass RC filter, which is the combination of both the low-pass filter feeding the high-pass filter, as seen in figure 3. We have the low-pass filter, which is everything from 0 to 20 kHz, and we have the high pass, which is everything from 20 hertz to infinity. And those thus are the upper and lower boundaries of the human ear, and that's what we're designing a bandpass filter towards. So our first one, we'll have this cutting off. The FC of this circuit will be at 20 kHz, and the FC of this one will be at 20 hertz and above, producing this plot right here. That's our bandwidth plot. Just for a review, notice that the 3 dB points on the graph at FL and FH, these are called your half-power poles and occur at the cutoff frequency for that circuit. The bandwidth of this filter is the high frequency minus the low frequency equals the bandwidth. And the first thing to consider when designing your bandpass filter is what you want your FH and FL to be. We are going to design a bandpass filter that will allow all the frequencies involved in human hearing to pass. Figure 4 illustrates the frequency response of the human ear. And it's from 20 hertz to 20 kHz. The graph tells us that our high pass filter's cutoff frequency is FL equals 20 hertz, while the cutoff frequency of the low pass filter is FH equals 20 kHz. Using this fact in equation 1, we can calculate our capacitance. The resistance will be determined by the input resistance needed as well as the output resistance needed, R2. Since to achieve maximum power transfer from the input to the output, aka load, we want R1 to equal R2. And when they have equal voltage across both of them, that is a half power drop or half voltage drop, and that will be your 6 dB point of your voltage drop. You can think of this by starting with the low pass filter, and remember that XC1 reactance is very low at all frequencies above the 3 dB point, and at FH equals 20 kHz sends the signal to ground. Anything above 20 kHz sends it to ground. And that XC is low at all frequencies above 3 dB point at FL equals 20 hertz. This causes R1 and R2 to act as a voltage divider and dropping the same voltage across each. This causes a 6 dB drop across the bandpass filter, voltage-wise. This can blow your mind at first, but just remember that the low-pass filter is everything from 0 hertz to 20 kHz, and the high-pass filter is everything from 20 hertz to infinity. So now we're going to open up our PTC Math CAD, calculate our C1 and C2, and continue from there. All right, we opened up PTC Math CAD Prime. This is the equation we're going to be using to solve for our capacitance. FC equals 1 over 2 pi times RC. We know what R is. That will be the equivalent of the cable we're using to transfer our signals in and out, and usually be 50 ohms or 75 ohms. The one thing we don't know is what C is. So let's enter what R is. R1 shift colon equals 100 ohms. And we have to use the units or the answer won't have the correct nomenclature on the output. So we go down to resistance, it's 100 ohms. R2, shift colon, is also 100 ohms for perfect power transfer. Go down to resistance again, find the ohms. Then we know what our low pass frequency is going to be. So we'll say LP FC shift colon equals 20 kHz. Bring it over to here. And you have to have the units correct, or like I said, the nomenclature of the answer will be wrong. Okay, HP, the high pass frequency cutoff, shift colon, is 20 hertz. So this is going to pass everything from 0 to 20 kHz. And after that to 20 kHz, it'll have a 3 dB drop. This, which is 20 dBs per octave, per decade, excuse me. Then the high pass frequency cutoff is 20 hertz to infinity. That's why it's the high pass filter. So we have our values that we need. We know that we'll substitute this in for this, bring the FC down into the denominator, and bring the capacitor up to the, and we'll bring the capacitor up to be on the left side of the equal sign. So we'll solve for C1 first. C1 shift colon equals 1 divided by 2 times pi times R1 times LP FC. Come down to here. We'll say C1 equals, and there it is. We have our nomenclature correct. That's farads. It's 7.958 to the negative eighth. That is not a common denominator in capacitors. Nanofarads is. So let's put this at a negative 9. That means we'll move the decimal point over one more place. So this tells me I have the decimal point moved 9 places to the right of the decimal point. So that makes that a 79.58 nanofarads. So let's solve for C2 now. C2, shift colon, equals 1 divided by 2 times pi times R2 times HPFC, which is 20 hertz. Hit enter, then come down to here, say C2 equals, and it equals 7.9 to negative 5. Well, that's not common. Microfarad is, which is negative 6. So this will be 79.58 to the negative 6, or 79.58 microfarads. And there you have the solution to all your capacitors. I want to show you what happens when we get rid of the correct nomenclatures for the resistance. See, you get a Siemens instead of what you would get as a farad. So that's your energy stored. So let's go ahead and put that on there. Come back up here. Just want to show you that in case you run into that. And see how it goes right back to the farads. Okay, that's our calculations for the capacitance. We now will build the circuit, just a low-pass filter here, because we're going to actually build the real circuit and then use real test equipment to calculate and build our Bode plot. Okay, that's it. Thank you. Okay, open up your QUCS. There we go. I've already built the circuit, so we're going to use it again, the RC low-pass circuit equations. But I'm going to show you where to get everything here and how to construct this schematic and run this simulation. We need to have, this is the same as the other one, but we need to change our resistor to be correct and our capacitor to be correct. So looking at our PTC Math CAD results for the capacitor, we know it needs to be 79.6 nanofarads. So we go to components. We get our capacitor, bring it over here, drop it. Just drag and drop. And you'd have to rotate this to get it to look like this. And then we would edit the properties and set it to 79.6 nanofarads. We don't need to do that though here. Delete that. We do the same thing with the resistor. Drag it over, drop it, rename the resistors by editing, right click, left click, edit properties, and then assign the resistor value that we want for that. We also want to name our nodes. This is our VN node, so we come up to name. We bring that over to here. We attach it to that node, and then change the A to VN. Do the same, do it again. And tag the V out node, just right, because the voltage drops across the capacitance, and then rename it V out. And we need a voltage source. So we come to here, we go to sources. We want an AC voltage source. We drag that over to here. We edit the properties here. And keep everything else the same. We want 1 volt VN. We renamed it to VN. And then we wire it together. But that's all done, so we're just going to move on. So we need to do a simulation. So we go down to the simulations. We're going to do an AC simulation. We bring that over to here. We right click on the AC simulation, edit the properties by left clicking on that. And then we set this up to be a logarithmic. And from 10 hertz, which will be, just make this a 10, get rid of the G for gigahertz, go down to here, make that a 20, change the G to a K, making that kilohertz. We're going to change this to 300 points. And so there's our simulation that we'll be using, and that will drive the simulation. But we're going to use this one. We already got it. But you need to have equations. So let's run the simulation real quick. That's going to populate V out and V in. And so that allows us to edit our equations. So to do the equations, you just hit edit properties. And these are the names that you come up with. You can name them anything you want. But these are functions inside QUCS. So, and that why this name has to be on this circuit. This name has to be on the circuit, as well as this name has to be on the circuit. We want to know the dB of the voltage out. So we just chose this as our name. And then this is the equation, dB parentheses of whatever you're going to do, and we dot voltage. Same with the V out phase. We do a phase of V out dot voltage. And the same thing with current, and that's the imaginary dB. We just named that, and it's dB, the current of the voltage in, the dB drop of that, and then we want to do the phase of that current, the voltage in phase. We built the table. We want to export all our data to a data set, but we don't want to display it. These we want to display. And that's our equation 1. Okay. So now we have these equations. We need to run it to build the tables that we're not displaying. We know we don't have any errors. We hit F2. We get nothing's changed, so there's nothing was done. We have 0 errors. We come back to here. Now we're going to construct our graphs. These are Cartesian graphs. So we bring that over to here, and we'll have all this to select from. This is in that table we exported. So our first one we want to do is the voltage out in dB. So we do voltage out. We're going to have a red colored trace. We're going to change our properties. The x-axis is frequencies. Frequency. The x is V out. And dB. The color is red. Oh, let's see. We'll just keep that normal. The style is solid. We're doing a logarithmic x-axis only. And then we say we want to show the grid, and we hit apply. And let's see, there's our graph. And it worked perfectly. It's not big enough to show the 3 dB like this one was, but as you can see, the 3 dB point is right here. And you can see in this graph, if we go click on the graph, right click, left click, edit properties, you can see that we're doing the V dB out right there. Our properties is frequency, V out in dBs, show grid, we're doing logarithmic x-axis grid. Hit OK. Now we do that on all these. I'm going to delete that because we don't need it. I didn't want to delete both of them. Okay, let's see. So I undid that. Control Z removes any errors that you might have done. So this is going to be current in the linear scale. So we look at this, and here we have VN, which we got from right over here. We just double clicked on that. It populated it into here. We come over frequency, current on a linear scale. That's what we're going to name it. And again, we show grid, solid line, logarithmic cell. Okay. And we get this. And you do it to the next two. Right? The next two items. Try to do that on your own. And now that'll be the end of that. Everything worked fine. We're going to go to and actually build the circuit. Thank you very much. Okay, I was going to go right into the physical lab where we actually create the circuit and use test equipment to see the graphs that we have calculated and simulated, but it's going to make this way too long. So that is going to be the next video, video 115. So please watch that. You'll get a lot out of it. We're going to set up the oscilloscope, the spectrum analyzer, the sweep generator, the circuit itself, and do what we did here through QUCS, but do it physically, actual stuff. And I'll show you the equipment I'm using, where to get it, and how much it costs. Okay, it's going to be fun. We'll talk later. Bye. Don't forget to select subscribe and hit the like button if you enjoyed this video.